All right, let's get right into it. We all want our code to be faster, right? More efficient. But how do you even measure what fast really means? Well, for this explainer, we're going to lean on Jay Wengrow's amazing book, A Common Sense Guide to Data Structures and Algorithms, to really get to the bottom of it.
And that's the whole point, isn't it? This isn't just some theory you learn in school. This is practical stuff. It's the difference between an app that feels snappy and one that has you staring at a loading spinner wondering if it crashed. And you've probably wondered about this, right? You can have two chunks of code that do the exact same thing, but one is instant and the other, well, it takes forever. What's actually happening under the hood to make them so different? That is exactly what we are going to unpack.
Now look, if words like algorithms or data structures make you a little nervous, don't be. Like the author says here, it all comes back to really simple common sense ideas. You definitely don't need a math degree to get this. Our goal is to break it all down using just that, common sense. So, to get our hands dirty with this, we're going to zoom in on one of the most basic building blocks in all of programming, the humble array. It's the perfect starting point for our investigation into what makes code tick.
So what is an array? At the end of the day, it's just a list. Seriously, think of it like a shopping list. We've got our items here, from apples to elderberries. Each one has its own little slot, its position, which we call an index. And in the world of programming, we almost always start counting from 0. That's it. Simple, right?
Okay, so to really figure out how efficient an array is, we need to look at the 4 basic things we can do with it. We can read an item from a specific spot, we can search for a value, we can insert something new, or we can delete something. The speed of these 4 operations, that's everything. That's what tells us if our code is going to be fast or slow.
But how do we actually measure that speed? This is where things get really interesting, because we have to change how we think about it. We're going to toss out the stopwatch. Instead, we're going to count steps.
And why would we do that? Well, because measuring in seconds is just flaky. An operation that takes 5 seconds on my old laptop might take less than 1 on a brand new supercomputer. Time depends on the hardware. But the number of steps? That's a solid, consistent number. An operation that takes 5 steps is always faster than one that takes 500 steps. It doesn't matter what computer you're on. And believe it or not, this whole idea of counting steps actually has a fancy name. It's called time complexity. It sounds intimidating, I know, but it's really just a formal way of asking, how many steps does it take to get the job done? Okay, so we've got our new mindset, we're counting steps. Let's actually put it to work. We're going to figure out the cost in steps for each of those 4 array operations, and we'll start with reading. So if you know the index of what you're looking for, how many steps does it take to read that value from an array? Just 1. A single step. That's insanely fast. But wait a minute, how on earth is that even possible? To get it, we need a quick peek at how computer memory works. You can just picture it as a giant grid of boxes, or cells. When you make an array, the computer goes and finds a nice, continuous line of empty boxes and sets them aside just for your array. And just like every house on a street has a unique address, every single one of those little cells in memory has its own unique address. It's just a number, but for the computer, it's the secret to finding things in an instant. And here is where the magic happens. The computer knows the starting address of our array. Let's say it's 1010. So if we say, hey, give me the item at index 3, it does super simple math. It takes the starting address, 1010, adds the index, 3, and gets 1013. It can then jump directly to that address and grab the data. One shot, no searching, no fuss.
Okay, but what if you don't know the index? What if you just know the value you're looking for? Like, you need to find dates in our shopping list. Well, now we're playing a whole different ballgame.
Without an index, the computer has to go one by one by one. This is called a linear search. So let's count the steps. Step 1, check index 0. Is that dates? Nope, that's apples. Okay, on to the next one. Step 2, check index 1. Is that dates? No, bananas. Keep going. Step 3, index 2. That's cucumbers. Still not what we're looking for. And finally, step 4, at index 3, bingo, we found dates. So that search took us 4 steps. Now, compare that to the single step it took for reading. It's a huge difference. And think about the worst case, right? What if we were looking for elderberries at the very end of the list? Or worse, what if we were looking for something that wasn't even there?
The computer would have to check every single item. So for an array that has n items, the worst case for a search is n steps. The bigger your list gets, the longer that search could take.
So searching can be pretty slow. What about our third operation, insertion? How many steps does it take to add a new item to our list? Well, it turns out it really depends on where you're adding it. You've got your easy case and your hard case. If you're just tacking an item onto the end of the array, no problem. That's one step. The computer just finds the next empty slot and drops it in. But if you want to insert something at the beginning or right in the middle, oh boy, that is a whole other story. Just look at this mess. To stick figs in at index 2, we can't just write over cucumbers. We have to make room. So first, elderberries has to shift over. That's step 1. Then dates has to shift. Step 2. Then cucumbers. Step 3. And only then, on step 4, can we finally put figs into that newly empty slot. You can see how this gets slow really, really fast.
So let's just put it all together on one table. This pretty much tells the whole story of the array. Reading, it's our superstar, always just one step. But then look at the others. Searching, inserting, and deleting, they all have a worst case that's tied to n, the number of items in the array. As that array grows, the potential cost, the number of steps, grows right along with it. And that leaves us with a really important question. If an array is so great for reading, but can be so slow for searching and inserting, what's the alternative? What could possibly be faster? Well, that is the entire reason other data structures even exist, to solve these exact problems and give us a faster way to handle our data. And that's the next step on the journey to writing truly efficient code.